This video is to prepare kids in Chem 111 for the final exam. This is part 3 of the review. We'll be dealing with density, classifications of matter, the periodic table, and naming compounds. Okay, so with density, the equation for density is mass over volume. So if we calculate the density of a material that has a mass of 52.457 grams and a volume of 13.5 centimeters cubed, we can figure out the density by plugging it into this equation. So density is equal to 52.457 grams over 13.5 centimeters cubed. We divide that out and it comes out to be 3.8857 grams per centimeter cubed. If we look at our numbers in the equation, once again, this is going to be a multiplication division rules because we're dividing mass divided by volume. So we're going to look at the quantity of significant figures here. There's 3 here, and there's 5 here. So we're going to round it off to 3 significant figures. So this 5 rounds the 8 up to be 3.89 grams per centimeter cubed. Let's try another density question before we go on. Pure gold has a density of 19.32 grams per centimeter cubed. How large would a piece of gold be if it has a mass of 3.18 times 0.97 grams? So as we're looking at this, density is equal to mass over volume. The density is 19.32. The mass is 318.97 grams over X. I chose this one for the review because this is one of the harder ones, because a lot of times the students get confused when the X is on the bottom. So to get the X out of the bottom, you're going to multiply it across. So that becomes 19.32 grams per centimeter cubed times X is equal to 318.97 grams. Now we need to get grams by itself, so we multiply both sides by 19.32. Those cancel. The grams here cancel, so we're left over with centimeters cubed. Divide that out and it becomes 16.5098. We have 5 significant figures here and we have 4 here, so that means we're going to want 4 in the answer. So that becomes 16.51 centimeters cubed. Alright, so let's move on to the classification of matter. I'm not going to give any examples of these. I'm just going to basically show you how to do them. You're given a piece of matter. That could be a glass. It could be peanut butter. It could be an apple. It could be absolutely anything. And you have to identify what it is. So first thing you want to ask yourself is whether or not it's a pure substance. Is it a mixture or is it pure? If you're given the exact chemical formula or the chemical name, you're pretty much guaranteed it's a pure substance. Because a compound is 2 or more elements bonded together. If you're given a specific name of an element, such as gold or silver, that you can find directly off the periodic table, then you know you have an element. And since you're given a periodic table at all times, it doesn't hurt to go ahead and check that if you need to. Now, if what you're given doesn't fall into that category, you probably have a mixture. So that means you have to identify whether it's a heterogeneous or homogeneous mixture. You might also hear homogeneous pronounced homogeneous. It's pronounced both ways. if you see the word solution there, you automatically have a homogeneous mixture. Because solution is the term they use. It's synonymous with homogeneous. So with the homogeneous mixture, you want to see if it's mixed evenly throughout. And the little question that nobody seems to tell you is that homogeneous mixtures will not separate. Whereas heterogeneous mixtures will. What I mean by that, if you make sugar-free Kool-Aid and you put it in the fridge, the first glass of sugar-free Kool-Aid and the last glass will taste the same. If you have sugared Kool-Aid, where you put too much sugar in it and it drops to the bottom, some of the sugar has settled out now. So the first taste of Kool-Aid and the last taste of Kool-Aid will not taste the same, because the ones on the bottom will be sweeter because of the extra sugar. Another example is with peanut butter. If you let peanut butter sit there too long, eventually the oil from the peanuts will rise up to the top. Because of the fact that it separates, that means it was never a homogeneous mixture. It is actually heterogeneous, even though it may look the same throughout. And then the other thing for heterogeneous is whether or not it looks the same. So it looks different every place you look at it. And I spelled it wrong. So what I mean by that is if you have just basically an apple. Let's think about an apple. If you cut an apple in half, you have the core in the middle, you have the meat of the apple, the white part in the around the core, and then you have the skin. Everywhere you look at it, it doesn't look the same. So therefore, that's a heterogeneous mixture. It's not just a single element or single compound. That's an apple compound. That doesn't exist. So you automatically know it's a mixture. And the fact that it looks different everywhere you look at it makes it a heterogeneous mixture. Now, how do we separate mixtures? There's 5 different ways that we're going to talk about. Magnetic attraction. That's if you take a magnet over something and a couple of the filings get picked up because of it. Paper chromatography. That's when you start separating out the colors, or you start separating out substances based on its weight and its polarity. Evaporation is when you let it sit there and some of the liquid comes off. Filtration is like a coffee filter. We're taking solid pieces out of a liquid. And distillation is when you boil it and you separate it by the different temperatures that it boils, boiling points. Make sure you memorize the different parts of the periodic table. We have the alkali metals, alkaline earth, transition, the boron family, carbon family, nitrogen family, oxygen family, halogens, and noble gases. And then at the very bottom, that have actually been excerpted from the middle, is the lanthanide and the actinides. We can tell a lot from the periodic table, such as the symbol, the atomic number, the number of electrons. There are certain things that you can't look at the periodic table for and just automatically get. For instance, if I look at the periodic table, here's aluminum, its symbol is Al. So I can put Al here for the symbol. I can also look at the periodic table and see that the atomic number is 13. Notice that there's 2 numbers here. One's a whole number, one's not a whole number. The atomic number is always the whole number. And the atomic number and the number of protons are 100% of the time the same thing. So I can put 13 in there for both of them. The mass number is the protons and the neutrons added together. So is these 2 lines added together, so 13 and 14 is 27. Now here, it didn't say anything about a charge, so that means that the electrons will be the same as the protons. So charge, right here, is the protons minus the electrons. The atomic mass is the average of all the isotopes with its relative abundance, 26.98. Notice that the atomic mass and mass number are very, very, very similar, but they are not the same thing. The mass number is for a specific isotope, whereas the atomic mass is the average of all the isotopes. All right, so let's try it again. AR is right here. It's argon with the atomic number of 18. Because the atomic number is 18, that means the protons are 18. Notice this time I gave you the mass number. So that means that if the protons and the neutrons add up to be 41, if I subtract 18 from that, it comes out to be a neutrons of 23. The number of electrons, it does not have a charge here, so that means it's going to be the same as the protons. Finally, we can look at for the atomic mass, which is 39.948. Once again, notice that the atomic mass and the mass number are not the same number. Mass number is for a specific isotope, where the atomic mass is the average of the isotopes. Alright, so for naming compounds, here's just a flow chart on how to work your way through these problems. First of all, you have to determine if it's an ionic or a covalent compound. You do that by determining if you have a metal there, or if you have NH4+. If you do not have a metal, you have a covalent compound. So is it an acid? In other words, does it start with a hydrogen? If yes, you have an acid. So it's going to be H something, so we had to figure out what that something is. If it's a halogen, you're going to have hydroic on it. So hydrobromic, hydrochloric, hydrofluoric. If it's not a halogen, you have a polyatomic ion. So for the ions that end in 8, you're going to change it to ic. So sulfate becomes sulfuric. Nitrate becomes nitric. If it ends in ite, you're going to change it to us, O-U-S. If you do not have an acid, you're going to use prefixes. So that's the mono, di, tri, tetra. Notice if the first atom is 1, you do not use mono. The second element ends in ide. So take the stem word, which is usually the first syllable, and end the rest with ide. If you do have a metal or ammonium, that means you have an ionic compound. The positive ion is always first. So what's the positive ion? If it's ammonium, you drop down and figure out what the negative ion is. If it's not ammonium, it could be a type 1 or a type 2. Type 1 is the type where you can look at the periodic table and determine its charge. So if I go back here, these are the type 1s. These are the type 2s plus the ones in the carbon group. If you do have a type 2 where you can't figure out the charges by looking at the periodic table, you need to use a Roman numeral. Then you use the name of the atom, and if it's a type 2, you put Roman numeral. If it's a type 1, you move on. Then you figure out what the negative ion is. If it's a monatomic one, you end it in ide. If it's polyatomic, you figure out what the polyatomic ion is. Remember to memorize your polyatomic ions. You will not be given a list of those on the test. So let's do some practice ones. NH4 is ammonium. And it ends, and it's bonded to chlorine, which becomes chloride. Cu3P. So copper is here. It's a type 2, which means that you need the Roman numerals. So copper something, P is phosphorus, so phosphorus becomes phosphide. In order to figure out the charge, you're going to uncross these numbers. So this 3 goes here, and this invisible number 1 goes here. We look on the periodic table and we look for the anion. Here's phosphorus. It's in the -3 row. So that means that this -3 here is right, which means that copper really is a charge of 1. Let's go the other way. Disulfur dichloride. Di means 2, so we have 2 sulfurs. Di means 2 chlorines. Al is aluminum. It's right here. It's a type 1, so I don't need Roman numerals this time. Cn is a polyatomic ion. It's cyanide. Alright, let's do a few more and then we'll be done with this video. Lead, Roman numeral 4, sulfate. We know lead is Pb. That Roman numeral 4 tells me it has a +4 charge. Sulfate is SO4, 2-. Once you figure out the charges in the ions, you want to crisscross the charges. Notice that 2 and 4 are both divisible by the number 2, so I'm going to reduce it down. I reduce down the ionic, I do not reduce down the molecular. So if it has prefixes, don't reduce it. So it should be PbSO4 2. So notice that this is a molecular one, this is a covalently bonded one. It's 2 and 4 as well. We do not reduce that because it's molecular. We don't reduce the molecular. So 2 is di, N is nitrogen, 4 is tetra, O is oxide. So dinitrogen tetroxide. I is iodine. Notice the first one here is single. There's only one atom there, or one atom there. So I don't have to worry about the prefixes. I don't use mono for it. 7 is hepta. And F is fluoride. Finally, we have sulfur tetrachloride. So sulfur, there's no prefix here, so it's a 1. Tetrachloride, chloride is Cl, tetra means 4. And that's the end of this review.